in chapter 5. Okay, so in calculus, the natural log function is the dominant function. I know nobody likes it, but that's what we use. We don't use base 10. It's the natural log function. Okay, because the derivative is fairly straightforward for the natural log function. The derivative is not as straightforward for any other log base, but the natural log derivative is fairly straightforward. So that's the function we will use, okay? But we need to review so the natural log function, you remember this, ln? Remember that? Logarithm natural, S. Okay, so properties of logs. Let's go over the properties of logs. So what's the natural log of 1? If you log the number 1, any base, zero. Remember that from 4 months ago? If you log the number 1, it is 0. Okay? If you have two, so remember the numbers that you're logging are called arguments. If you're logging two numbers that are multiplied, what can you do with the arguments? You could add them. Natural log of A plus natural log of B. All right. So multiplying the arguments is the same as adding the logs of each individual argument. If you are logging a number that is raised to an exponent, what can you do with that exponent? You can drop it down in front. N log A. Well, I shouldn't write log, natural log of A. Okay, and that rule we will use a lot because it makes our life easier. And if you are dividing the arguments, what are you doing? Subtracting. Natural log of A minus natural log of B. Are these ringing bells? They should be. I hope so. Okay, so let's do a couple of examples. You need to know those rules. If I have the natural log of the square root 3x plus 2, how can I rewrite that with no radical sign? Because we don't like radicals in calculus. We like exponents. So I can rewrite it as 3x plus 2 to the power of a half. And then what can you do with the half? Drop it down. We're not doing, we're just going to practice this for now because you're going to see later on, writing it like that makes your life way easier and you can get out of using the chain rule a lot of the times if you use logs. Okay? If I have something like this, then natural log x squared plus 3 all squared over x cubed x plus 1. I want to write this, I want to break this apart because this, so what we're going to do is we're going to use logs to benefit us. If I just gave you that and said take the derivative of that, that has got a chain rule and a quotient rule inside of a product rule. So you pretty much have all these formulas working together. That's going to be a bleep show. Okay? But if you log it, you can rewrite it like this and it gets really simple to do. Okay? So how do I break this up? We're dividing. So if you're dividing, you are subtracting. So the first thing you can do is go the natural log squared minus, now be careful about this part. I'm going to do it in steps. And I'm going to rewrite the square root as power of half. So we were dividing these, so I just broke them up into subtraction. This one, the 2 can come down. So I get 2 natural log x squared plus 3 minus, now these are being multiplied. So what can I do? If you're, sorry? Bring them. I want to break them apart. You're adding them, right? You can't drop exponents yet because they have different exponents. But because these two are being multiplied, I can add them together. But you have to remember that whole thing is being subtracted. So put it in brackets. And then the final step will be to dump the negative in and drop the exponents. There you go. Okay. Is that okay? So we're just reviewing our log rules and taking something that is like built up into a gong show here and breaking it apart. That's all we're doing right now. We're not even doing calculus. We're just practicing this because we're going to use this to do derivatives. Okay? Any questions? All right. I'm going to give you some practice questions then. Page 325, 17 to 33 odd. Please. And then we'll get into the actual calculus. Yep. Okay. What is the natural log function? Now, it makes more sense once you know integration. And it looks a lot cleaner than what I'm drawing here. I've left, well, and we'll talk about this. So the natural log function is defined as the area under the curve 1 over x from 1 to x. So what the heck does that mean? It means when you go, well, I don't want to do it. If you say the natural log of 2, and you do that in your calculator, what's the natural log of 2? Natural log of 2 is 0.693. Bunch of other stuff. Who cares? That means you don't have to draw this if you don't want to. This area is 0.693. That's all the natural log function is. It's the area under the curve of 1 over x from 1 to 2. This is one of the reasons. So there's another. When I say the natural log of 1, why is it 0? It's from 1 to 1, right? So you're like here. There's no area under that curve, right? You haven't gone anywhere. So that's one of the reasons the natural log of 1 is 0. Well, that is the reason the natural log of 1 is 0. So this is a weird sort of concept for kids to understand. It doesn't matter for us right now. Once we know integration, this will come back into play. But I just wanted to give you what the actual natural log function is. Now, the derivative, I can't, it's hard for me to show you where the derivative comes from the natural log function because you need the integral definition. Well, you don't need it, but it helps to have the integral definition. We don't know what integrals are yet. So I'm just going to give you what the derivative of the natural log function is. Okay, and we'll come back to how you get it later on. So the derivative of the natural log function of the ln of x is equal to, are you ready for it? 1 over x. That's the simplified version. This is the one you're going to use more often. The derivative of the natural log of u. U is some function, okay, is 1 over u times u primed. So most people think of it this way, u primed over u. This is the one we're going to use most of the time because we're not going to be differentiating x, natural log of x. We do other functions, more complex functions. So knowing this, natural log derivatives are actually quite simple. So go away. If we look at, we'll start with a straightforward one. The derivative of the natural log of 2x. So, u is your argument. The first thing you do is you put 1 over your argument, 1 over u. So we just go 1 over 2x times the derivative of u. What's the derivative of 2x? 2. What happens to the 2's? They cancel. So you get 1 over x. You're done. Well, yeah, you could do this. You could do product, or you could break it up if you wanted to. You could say that this is actually. Does everybody agree that's the same thing? Right? I just broke up the arguments. Natural log of 2 is a constant, right? What's the derivative of any constant? 0. What's the derivative of natural log of x? 1 over x. So you can do it that way if you want to. All right, let's do something more interesting. So, we're doing the derivative of that. I should have put d dx in front of it. There we go. The derivative of the natural log of x squared plus 1. What's my argument? X squared plus 1. That goes in the denominator. What goes in the numerator? The derivative of the argument. That's what this is. The derivative of the argument. What's the derivative of x squared plus 1? It's just 2x. You can't simplify it or anything. 3. Derivative of x times the natural log of x. So, what rule do we need to use here? I heard somebody say it. Product rule. Why? Because there's two functions being multiplied together. There's this function and there's this function. So, product rule says derivative of the first function. What's the derivative of x? It's just 1 times the other function plus the derivative of the other function. What's the derivative of the natural log of x? 1 over x times the other function, which is x. What's x times 1 over x? 1. So it's just the natural log of x plus 1. Thanks, Griffin. Is that okay? What about this? Natural log x cubed. There's a couple different ways to do this. Sorry? That's what I would do, right? If you have an exponent on the argument, you can drop that down. Do you care about, well, you care about them, but do you need to worry about the constant when you're doing a derivative? No, so I can just put the 3 there and then do the derivative of the natural log of x. What's the derivative of the natural log of x? 1 over x. So really I could just write 3 over x. You're done. You could, if you don't want to drop it down, you could do this. The derivative of the, or 1 over the argument, which is x cubed. What's the derivative of x cubed? 3x squared. And then if you simplify that, you get that. So you get the same thing. It's your choice. What if you have this? Not quotient. It's chain rule, right? Because you can't drop the 3 down because the 3 is not on the argument. It's a chain rule. Chain rule says outside derivative. So the 3 falls down times the inside function, but you take 1 away, so that becomes power of 2. Times the derivative of the inside. What's the derivative of the natural log of x? Times 1 over x. And you're done. I mean, you can clean it up. You could write 3 natural log of x all squared over x like that. Also, just for notation purposes, if you're squaring the natural log like this, just like when we did it in trig, remember in trig when you do the, if you're going to square it, you can put the square on the trig part of it. You can do the same thing for a natural log. So you could write that means the same thing. The squared here means you're squaring the whole thing. If I want it on the argument, I have to put the square on the argument. So just be careful about that notation. Thank you. Okay. 6. Derivative of natural log root x plus 1. So, do we like radicals? We like exponents because we know how to deal with exponents. So I can rewrite this. And then what can you do with the exponent? You can drop it down. And then if you're doing the derivative of that with the constant doesn't matter, so we can just write the 1/2. The argument goes to the denominator. What's the derivative of x plus 1? It's just 1. So the answer is 1 over 2 times x plus 1. So this is getting us away from the chain rule. Okay? And we'll do one final one. If I have, if f of x is equal to the natural log that's ugly. Like, that's gross. Doing the derivative of this would be a nightmare. Because what you'd have to do, if you were just going to do it without using log rules, is it's 1 over the argument. This is the argument. So your first step is 1 over this junk times, and then you have to do the derivative of that, which is going to be a chain rule, product rule, quotient rule question. That's going to get real big and gross. But we have log rules. So what's the log going to allow me to do to the numerator and the denominator? If you're dividing, you are doing what? Subtracting. So we rewrite it at first. We go, okay, this is the natural log of x times x squared plus 1 all squared minus, I'm going to turn the denominator into a fractional exponent. To that. Now what do? We still want to simplify. Separate this, and then we're going to start dropping exponents. So the next step is going to be natural log of x plus 2 times the natural log So now we have this. We've broken it into 3 separate parts. Now we can do our derivative. And because it's all being added, you just do each one separately. What's the derivative of the natural log of x? It's 1 over x. This part, b. I don't know why I'm calling it b, but the 2 is a constant, so I don't care. Put that out. And I should say this is f prime. 1 over x squared plus 1. And then the derivative of x squared plus 1 is 2x, which goes in the numerator, minus 1/2, the constant just keeps out, over 2x cubed minus 1. The derivative of that is 6x squared. And then you just want to clean it up. So we get 1 over x plus 4x over x squared plus 1. This 1/2 and this 6 will turn into a 3. And that's it. So something that's big and ugly, if it has a natural log in it, you separate it out into each individual term, and then you just do each term separately. Okay? That's the advantage of this. It gets us away from using chain, quotient, blah, on all that. Okay? Are there any questions about this? All right, so rewrite them and then do the derivatives. 325, 41 to 59, odd, and 73, please. Boom. And that'll be it for today.